So now we will update global best as the current position of x1 because it has better fitness than the global best seen in previous iterations. So this position will no longer be the global best, rather this position from now on will be considered the global best of the swarm. Now let us understand the working of PSO and GA algorithms individually, and then we will see how the hybrid of GA PSO algorithm works. So first let us understand the working methodology of PSO algorithm. The PSO algorithm basically mimics the social behavior of birds and fishes. It was developed in 1995 by Kennedy and Eberhard. In this algorithm, a random population is initialized and each individual in the population is called particle. Each particle has some position and velocity associated with it. The positions of particles represent the possible solutions and the velocity of particles represent the rate of change of next position with respect to the current position. The particle swarm optimization algorithm is a memory based algorithm, that is, it will have the personal as well as global memory. Each individual in the population will retain the memory of its personal best experience. By personal best experience, we mean that each individual will retain the memory of the position at which it has found its own best fitness value up to that point or up to that iteration, and the position up to that iteration at which it has found its best fitness so far is termed as personal best. And the algorithm, or we can say and the swarm as a whole, will retain the memory of global best experience. By global best experience, we mean that irrespective of which individual, the swarm will have the memory of the position of best fitness value of whole group, of whole swarm, no matter which individual has found that position, but it will remember the position at which the best fitness value up till that point has been seen by the group, and the position of the global best fitness value is termed as global best, or we can say G best. So let's say that in the algorithm we have three particles, and after three iterations these are the fitness function values of the three particles. Since we are using the algorithm to minimize the objective function, so the less is the fitness value, the better the position is for us. So here we are trying to find out the position which has the least value of f. So for the first particle, as we can see, among the three iterations, this has the least fitness value. Similarly, for the second particle, among the three iterations, this one has the least fitness value. And similarly, for the third particle, this one has the least fitness value. So the personal best of the three particles will be 2.045, 7.562, 9.563. This is the personal best value of the particle. Personal best is the value which has the best fitness seen by that particular particle in its history. And now among these personal best values, this value of 2.045, this is the least fitness value of the entire swarm, of the entire group history. This is the least fitness value. So this is the global best value, 2.045. This is the global best value. The best value, the best fitness value seen by the swarm in its history so far. Each individual updates its position and velocity under the influence of three factors. One is its previous direction of movement, that is its previous velocity. The other one is its personal influence, that is the memory of personal best. And the third factor is the global influence, that is social influence, that is the memory of global best. So each particle will be attracted towards its own personal best, and it will also be attracted towards the global best of the whole group, as well as it will also move under the influence of its previous, or we can say current velocity, that is the previous direction of movement, and the next velocity will be decided by these three factors adding up, and we will get a new vector which will be the sum of the three vectors. And when we add this velocity to the current position, we will get the next position. So this is the diagrammatical representation. So let xit be the position of ith particle at tth iteration. So as the algorithm is, the particle in the previous iteration, that is t minus 1th iteration, it would have been at some other position, and it has reached this position in the tth iteration by adding some velocity vector. So this is the current velocity vector, that is, this is the velocity vector of the previous iteration, which once added to the position of previous iteration made the particle reach this position. This is the personal best of the particle. This is the personal best of the ith particle. So this is the personal best of ith particle, that is this particle. And this is the global best position of the whole swarm or group, we can say. Now this vector is the position vector from current position to the global best position, and this position is the position vector from current position to the personal best position. And as I have told earlier, this particle moves under the influence of its current velocity, personal influence and social influence. So this vector, this red vector, which is omega into VIT, this is the vector in the direction of current velocity, that is the velocity of TS iteration, and this blue vector is the vector in the direction of personal best. As you can see, this vector is parallel to this vector, and this vector in black is the vector of social influence, that is, this is the vector in the direction of global west, and you can see this black vector is parallel to this vector. Now when we add these three vectors, we get this vector. So this is the updated velocity vector for the next iteration, that is t plus 1th iteration. And once we add this velocity vector of t plus 1th iteration to the current position of th iteration, we get the position of t plus 1th iteration. And mathematically, the position and velocity update is represented by these two equations. So velocity of ith particle at t plus 1 iteration is equal to inertia weight into velocity of ith particle at tth iteration, that is current iteration, plus c1 into r1 into personal best of the ith particle minus the current position of ith particle. Here this is also the free best of ith particle. And then the third term is plus C2 into R2 into global best minus current position of the ith particle at Cth iteration. Here W, as I told earlier, is the inertia weight factor. C1, R1, C1 and C2 are the acceleration coefficient. C1 is the personal acceleration coefficient and C2 is the social acceleration coefficient. R1 and R2 are random numbers between 0 and 1. Now let us understand the importance of inertia weight C1, C2 and R1, R2. Now this W, that is the inertia weight factor, it decides the influence of the current velocity of th iteration on the velocity of next, that is t plus 1th iteration. Hence, this W denotes the influence of particles' previous motion into the current motion. For example, if W is equal to 1, then particle's motion is fully influenced by its previous motion, while if W is less than 1, that is between 0 and 1, then the influence of the previous velocity on the next velocity decreases. So this decides how much this influence the previous velocity has on the next velocity. So this is the first factor. Now the second term is C1 into R1 into personal best of ith particle minus current position of ith particle at th iteration. Here C1 is the personal acceleration coefficient and R1 is random number. C1 decides the influence of personal best position on deciding the velocity for next iteration. And R1 basically decides the length of vector from current position to the personal best position. That is, as you can see, this is the current position of ith particle and this is the personal best position of ith particle. and this is the vector from the current position to the personal best position. If r1 is 1, then this whole length of vector will be added here, but by multiplying it with a random number which is between 0 and 1, a vector of length which has less length than this particular length is added to this current velocity vector. So this r1 decides the length of this vector which is parallel to this vector, and c1 decides the influence of this vector. The greater the value of c1, the more influence this personal best will have on deciding the velocity for next iteration. Similarly, the third term is c2 into r2 into global best of the group minus current position of ith particle. Again, c2 is the social acceleration coefficient and r2 is another random number, and r2 decide the length of this vector which is parallel to this vector of between the current position and global best position. So this is the length of vector from current position to global best position, and when we multiply it with a random number between 0 and 1, some other vector of length less than this particular length will be added to these two vectors, and the sum of these three vectors is the new velocity vector for the next iteration. Again, c2 is the social acceleration coefficient, and the higher is the c2, the more influence this global best position of the swarm will have on the velocity of the next iteration for that particular ith particle. So the velocity update equation, or we can say the velocity update vector for the next iteration, is decided by the three factors. One is the current velocity, other is the personal best influence, the third is the global best influence. Diagrammatically, the three factors are represented by these three vectors. This is the current velocity vector, or the vector parallel to the current velocity. This is the vector parallel to the vector from current position to the personal best position, and this is the vector parallel to the vector from current position to the global best position. Adding up these three vectors, we get the updated velocity vector for the next iteration. And then for the position update, it is a very simple equation. We simply add the velocity vector of the next iteration to the position of previous iteration. That is, we add the velocity vector of t plus 1th iteration to the position of tth iteration, and we get the position of t plus 1th iteration. Diagrammatically, we can see this is the velocity vector of t plus 1th iteration, and this is the position of tth iteration. When we add this vector to this current position, we get the next position of t plus 1th iteration. So this is how a particle moves and updates its position and velocity under the influence of current motion, under the influence of personal experience, under the influence of global best experience. So this is basically the PSO algorithm. Before we move further, let us discuss a few more things about C1 and C2. As the velocity for next iteration depends on these three factors, it is very necessary to balance the effect of these three factors so that any one factor does not dominate the other two factors. Here C1 and C2, which are the personal acceleration coefficient and social acceleration coefficient respectively, they are also called as thrust parameters of PSO. C1 expresses how much a particle has thrust on itself, while C2 expresses how much a particle has thrust on its neighbors. Now, if this C1 is very less as compared to C2, then the effect of this factor will be very less as compared to this factor, and the particles will be more attracted towards the global best rather than their personal best. What this will do, let us understand through another diagram. So suppose this is the global best and this is the x1 particle and its personal best. This is x2 particles and its personal best, x3 particle and its personal best, x4 and its personal best, x5 and its personal best. So if the effect of the third factor is much greater than the effect of second factor, that is if particles are attracted more towards the global best rather than their personal best, then it may lead to premature convergence of particles like this. Since the global best is a single point and more particles are attracted towards the global west, so they may converge at the global west. This is likely to cause the problem of the population getting trapped in local minima. The reason for that is as more particles are attracted, now this may cause the problem of getting trapped in local minima. The reason for that is that as the particles are more attracted towards the global best, which is a single point, so they will quickly accelerate towards the global best and converge on the global best, even though better solutions may be present in the search space, but they may not be able to explore the space effectively. On the other hand, let us see if this C2 is less as compared to C1. So if C2 is less and C1 is more as compared to C2, that is very much more than C2, then let us see what happens. In that scenario, in this scenario, the effect of this factor will be more pronounced than this factor. This will cause the particles to trust itself more and they will be more attracted towards their personal best rather than the global best. So if C1 is very greater than C2, then suppose this is the x1 particle, this will be attracted towards its personal best, x2 particle will be attracted towards its personal best, x3 will be attracted towards its personal best, x4 towards its personal best, x5 towards its personal best. And this may cause slow convergence, or it could may also be the case that the algorithm may not converge at all, because as the particles are more attracted towards their personal best positions rather than the global best positions, then they will roam about the search space more and will not converge at the global best quickly. So it is very, very important to balance the effect of attraction towards the personal best and attraction towards the global best, along with motion in the current direction of velocity. So we have seen what would happen if C1 is very, very greater than C2, or C2 is very, very greater than C1. Now, if both C1 and C2 are large, in that case, the particle's velocity will accelerate too fast. From the equation, we can see if C1 and C2 are very large, then this velocity will be very large. So if these two coefficients are very large, the particle velocities will accelerate too fast, and that may cause the swarm divergence, because the velocities will be very, very fast. The particles will roam around the search space very, very quickly. They may not converge at a point, rather they may continue roaming around the search space and may not converge. On the other hand, if C1 and C2 are very small, then the swarm convergence time will increase, as the particles will move very, very slowly. So in order to find the optimum efficiency, proper control on global exploration and local exploration is crucial. Hence, we decide the values of C1 and C2 close to each other, such that the C1 C2 values are not too much large and neither too much small. Generally, the optimal range of C1 and C2, as seen from the previous studies, is considered to be somewhere between 1.5 to 2.5. Generally, it is taken near about 2. In our algorithm also, we have taken C1 C2 both to be 2.3. So with this, I think the effect of C1 and C2 is clear. Now let us discuss about the first factor, that is inertia weight. Now this inertia weight decides how much the particle will move in the direction of its current velocity, or the velocity in previous iteration will influence the velocity of next iteration by what amount. That will be given by this inertia weight W. If it is 1, then the velocity of next iteration will be completely influenced by the velocity of previous iteration, and if it is 0 or very, very small, then the velocity of next iteration will not be influenced at all by the velocity of previous iteration. It will be influenced by the attraction towards global and personal best. Now, through the research studies, it has been found that keeping W constant is not a very good idea. So the inertia weight is varied as the algorithm progresses. The most common method of varying inertia weight, that is W, is by linearly decreasing the inertia weight. This is shown by the equation W equals to W max minus W max minus W min upon iter max into iteration. This is nothing but a linear equation in W and ITER iter, because W max and W min as well as iter max, they are all constants. W max denotes the maximum value of inertia weight. In our algorithm, we have set it as 0.9, W max we have set as 0.4. So the W max and W min are constant, and iter max is the maximum number of iterations or total number of iterations. So this is also a constant. Iter, iter denotes the iteration number, that is at the start of the algorithm when iterations are 0 or we are in the first iteration, then iter would be 0 because no iterations have been completed, and W would be W max, that is 0.9. When the algorithm is completed, that is when iteration number is equal to the maximum iteration value, then these two factors will cancel each other and the W would be equal to W min. Hence we can see that by this method we are linearly decreasing the value of W from 0.9 to 0.4. This is a very common method of varying W. Several other methods of varying W has been proposed. In fact, extensive research has been done to decide the optimal method of varying W for the best possible results. The other methods are logarithmically decreasing the inertia weight, sigmoid decreasing the inertia weight, exponentially decreasing the inertia weight. Linearly increasing inertia weight method is also being proposed, and several others. At least 10 to 15 methods are there for varying the inertia weight, but this linear decreasing of inertia weight is very commonly used in several problems, and it has been shown to give much good results. So in our algorithm we will also use the linear decreasing inertia weight method. One more thing to note about W, the inertia weight factor, is that a very high value of W means that the velocity of next iteration are greatly influenced by the particle velocity in the previous iteration. And since the velocities of different particles may be oriented in different directions, let's say these are the particles, and let's suppose x1 may have its previous velocity along this direction, x4 may have its velocity along this direction, x3 along this, x5 along this, x4 along this. So different particles may have their velocities oriented in different directions. So by keeping the value of inertia weight very high, what we are doing is that we are randomly roaming in the search space. This leads to slow convergence because we are roaming in the search space. The convergence is very slow, but at the same time it also helps in effectively exploring the search space. And since at the start of the algorithm we have no great idea about what are the best solutions or better solutions, so at the start of the algorithm we actually want to explore the search space as much as we can. Hence at the start of the algorithm we keep the value of W high, and as we proceed towards the end of the algorithm we want the algorithm to converge towards the best solution. Assuming that the algorithm has already explored the search space extensively towards the final iterations, we want it to converge towards the global best. Hence, we want the W value to be lower. That is why This linearly decreasing inertia weight is used in the particle swarm optimization algorithm, in which at the start we have W equal to W max, that is zero point 0.9, and as we reach the final iteration W equals to W min, that is zero point 0.4. We linearly decrease the value of W from zero point 0.9 to zero point 0.4, so that at the start we explore the search space effectively, and towards the end our algorithm is able to converge at the best solution. So this is about the PSO algorithm. Remember that every position in the search space of PSO algorithm has two things associated with it. One is the value of variables at that position, and other is the fitness value or the objective function value at that position. That is, let's say that our objective function is 2x square plus y cube. Now here x and y are the variables, or we can say decision variables, and f is the value of objective function. For different values of x and y, we will get different values of f, and we are actually trying to minimize this f value. So we are trying to find the optimal values of x and y such that the value f is minimized. That is our objective. So f is nothing but the fitness value, and x and y are the values of variables or decision variables. So every position in the search space has some value of variables associated with it. That is variable value. And it will have some fitness value associated with it. So this position will have some value of x and y and some value of f. Similarly, this position will have some other value of x, y, and some other value of f. This position will have some other value of x, y, some other value of f. So every position has different values of variables and different value of fitness associated with it. So when we refer to a point in the search space or position in the search space, we are actually referring to the values of variables and the value of fitness at that position. And hence the personal best can be defined as the position at which that particular particle has seen the best fitness in its own history. That is, personal best is the position at which the best fitness value in the history of that particular particle has occurred so far. And global best can be defined as the position at which the best fitness value has been achieved by the whole swarm. It does not matter which particle has achieved, but it is the best fitness value seen by the whole swarm in the entire history so far. That is the global best position. And the value at that position is the global best value. And at the end of each iteration, we will check and update the personal best position for each particle, and we will check and update the global best position for whole swarm. For example, let's say that at the end of t iterations, this is the scenario. These are the personal best values of the particles, and this is the global best value of the whole swarm. And let's say that at the next iteration, that is t plus 1 iteration, x1 reaches a position that has better fitness value than its personal best value till the previous iteration. So as soon as x1 reaches a position that has better fitness than its personal best, it will update the personal best as the current position. So this position will no longer be the personal best, and now from now on onwards, this position will be considered as the personal best by x1 until it finds a position which has even better fitness value than this position. So the position so the current position of x1 will be considered as the personal best, and the fitness value at that position will be considered as the personal best fitness value for x1. Similarly, we check for other particles as well. If any other particle finds a position that has better fitness value than its own personal best, then we will update that position as the personal best position of that particle, and the fitness value at that position will be considered as the personal best fitness value of that particle. In the same manner, we will check and update global best as well. Say for example, the position that x1 has reached now, it has not only better fitness than its own personal best, but it also has better fitness than the global best of the whole swarm. That is, this position is the best fitness position, or we can say this position has better fitness than any of the positions that any of the particles has reached so far in the algorithm. So now we will update global best as the current position of x1 because it has better fitness than the global best seen till previous iterations. So this position will no longer be the global best, rather this position from now on will be considered the global best of the swarm. So the fitness value associated with this position will be considered as the global best fitness value, and the position, this one, will be considered as the global best position until of course we find a position that has even better fitness than this position. Then we will update the global best and so on. So at the end of each iteration, we will continuously check and update the personal best of respective particles and global best of the whole swarm, and we hope that in the same manner we will towards the end of the algorithm reach the best position. That is, all the particles will converge at the global best, and that global best will be the global minima. In this is the manner in which PSO algorithm works, and this is how it converges to the global best in the hope that by continuous updating of personal best and global best positions, we have finally reached the, the global minima of the algorithm. So now we have seen the methodology of PSO. Now we will see the working of GA roughly. In detail, we will see when we code the GA portion of hybrid algorithm. For now, we will see the GA algorithm step roughly, and then we will understand how the steps of GA and PSO algorithm are together used to make this hybrid algorithm, and how this hybrid algorithm is working to find the better results than individual algorithms.